Hello, this is a two-part series with Ansys static structural and space claim. In the first part, I'll be building a system model of mid-surfaces on some of this geometry and using fixed joints to check the design of the 6 bolts holding this flat plate to this pipe structure. And in the second video, I will extract the forces and do a sub-model using this solid portion of the backboard and applying the deformation from the system model to the sub-model and applying the joint force to the hole using a bearing load. So let's get started on the first part of this is a static structural for the system model. We're going to pull in the geometry that we see here, which I've already set as suppressed half the geometry. And so we're going to simply speed up the demo by just reducing the number of joints that have to be made. And then we'll go back and do a second video on the sub-model for details around the peak stress, which turned out to be on this hole. So in engineering data, we do want a little bit of aluminum. So under general materials, we'll add the aluminum alloy. And then we'll go ahead and connect to the open backboard and open mechanical. So mechanical has opened and the geometry shows there's a few little pieces where the thickness is unknown because on all of the other geometry I used mid-surface, so it knew the thickness. On this I didn't, I just used the face of the solid to create the geometry that would interface with the size of the hole in the pipe. And so that's what we've got here. All the materials are steel except for the board, and so the backboard I'm going to flip over to aluminum. And now we're going to add some mass to this, which under the geometry we can insert distributed mass and assign it to this face. And I'm going to put 50 kilograms on there. So this is a backboard for a patient to lie on, and so if you have a 200 kilogram patient and the horizontal portion that they're sitting on is taking 100 kilograms and then the backboard is taking 100 kilograms, 50 on each side, and that is on that face, equally distributed. We're going to have symmetry. Let me try that again. Face. There we go. We're going to have a symmetry condition because we're doing symmetric loading on the symmetric geometry. In a real analysis, I would have done a full model, but for the purpose of the demo, we're going to use symmetry to speed up the demo, and that is to insert symmetry, and under the symmetry, insert a region, and in the region, pick a couple of edges, this edge and that edge, to be symmetric about the z-axis. So that is providing some supports for the model. The other supports are basically a revolute joint to ground in here, so that'll go under connections, insert a joint, and it's a body ground joint type revolute, and we're going to pick the two edges, and there we have a revolute joint to ground. So that's allowing, that's tying up 5 degrees of freedom, just rotation around that. And so we need one more constraint to prevent rigid body motion, and that is the constraint provided by the support arm, which we're not modeling. In fact, we will not even bother to model the U bracket because it's not the focus of this analysis. But what we'll do is create a coordinate system. Insert a coordinate system. Let me insert a coordinate system and use this face to place it. And the origin there is at the face. Actually, I could have put it a little further down, but I want the normal, maybe the principal axis of Z to be normal to the geometry. So now we have a Z-axis that is defined on that coordinate system, and maybe if we go look at space claim and show all, it's almost a 90-degree angle, so close enough that I will just restrain the Z motion of these two holes using a remote displacement. And so that can be under static structural, a remote displacement, and I'll make that remote displacement in the coordinate frame I just defined, and the Z component will have no translation, but it'll be free otherwise, and that'll just take away the rigid body motion. So since that can be applied directly to these two holes, I don't actually need the U bracket. So apply that. Ideally, I could move the origin of that coordinate system down to here, but it's the same result really. So we will now select that body and suppress it. We don't need to mesh that. So with that and that, all we need to do is 3 fixed joints to connect the backboard to the pipe, and we will be ready to go. We do have a little bit of a defect here. And the coordinate system is confused about where to put the geometry. Oh, because I used a face that I just deleted. So that is easily corrected by changing changing the geometry selection to global coordinates, so it just stays where it is. And also, the principal axis can be geometry, but we'll use this face instead. And I don't really care which way that points. The Z-axis is set to 0. So we've got our symmetry. We've got one joint down here and a remote displacement up there with Z equals 0. So the last thing is some joints to bolt this together, and that is most easily done with insert joint. And if we pick edges, we want that edge to be the reference, and then this edge, hold the control key, and that edge to be the mobile. There's the first joint. Z-axis is the normal, and a couple more. Insert a joint, reference, and control click, mobile. And last joint, insert joint, reference, control click, mobile. So that's all fully connected, and we have put some mass on. We need a load in the static structural, and that is a acceleration. in the Y direction. So we'll go with coordinate components, and we're going to do a 10G load. So there's 10 Gs, and that will pull the mass down. It's, I think, ready to solve. So we can do a quick check. I did create some shared topology here, but it doesn't seem to come through. So I'm going to go ahead and create a mesh with, say, 4mm element size and just generate that with all the other defaults. Okay, and it's finished meshing. And what I can see by the red color is that the shared topology is not working, but it is working well enough to have all those nodes line up. So we can use the mesh node merge group and tell it, look for any nodes that are got a 1mm on any edges, and generate the conditions. So 68 nodes were found, and if we now look at the mesh, that purple color tells us that those nodes are all connected. So we've got a full circle. So the joint which is picking up on these edges will give us a good connection. That is this joint here, and actually it was put on two edges, but if I extend the limits, I get the other half, which is more correct. And I think now we can risk a solve. And some of the things we want to know is the forces going through, say, this joint, which I happen to know is going to be the largest forces and the highest stresses in the backboard. So I want to know the forces going through that joint, so this probe will tell me those. And we might also look at the directional deformation in the Y direction, and look at the stress in the backboard. Yeah, I think just that body. So let's see if we can solve. You sometimes get this warning, even though when it solves, we'll know that it was a necessary warning. And here we do have the force going through that joint, 66 pounds in X, 283 in Y, and 147 in Z. We're going to use those forces in the next analysis. We're going to ignore the stresses here because there's really a bolt there, and if we look at the deformation, let's bump that up a little bit. The weight is sagging, and so it's pulling on that bolt, and so the stress should really be on this side of the hole, but it's not because it's a joint, and the joint holds on all the nodes. So in the next video, we're going to take these results and analyze them on just a little piece of the backboard. So we'll see you in the next video.